this now. If you go look at your test and you go look at the little section that says response to learner, I should have put like a graded copy of your test up in there. So like I spent a good amount of time grading these things. I've been staring at a screen for I don't know how long, but I spent a good amount of time grading these things. I hope you go and look and see what I wrote in your paper. I think I'm gonna give us like 3 minutes or something just to look at that to get people. Hope you're going to Blackboard, going and looking in the grade book. Should be something like comments or something if you click the test one. Are y'all finding it, hopefully?
Professor Stevens?
Oh, yeah.
It's not based on the test, but it's something about the homework.
Oh, yeah?
3A and 3B. So, I've been trying to submit it, like I submitted it the day of, and I'm just checking my grades right now, and I see that it did not submit, and I've been trying for about an hour to submit it, and I just can't submit it. Is there a way I can email it to you?
Yeah, shoot it to me in an email.
Awesome.
Just tell me you're having problems submitting. Just say I couldn't submit it. Here's
okay, thank you.
Because I'm like, to be honest, like I just got, I've been like grading your tests. So I haven't like even gotten around to like catching up on that homework yet. I'm a little bit behind, being honest.
Would there be a lag? This is also regarding homework, but would there be a lag in like updating the points in Blackboard? There is one homework assignment I emailed you about with an issue, and it says I got 100, but then it says 0 on the grade. I think that was for 1C and 1D.
Let me see. Yeah, let me double check. I'll make a note of it.
Okay, thank you.
I'll look for it.
Appreciate it.
You said 1C and 1D was the one you're missing?
Yeah, I'm pretty sure. I emailed you about it. I was like the had attached but didn't submit, and I sent you like the screenshot and stuff.
Or 2A and 2B is what you sent me, is what it looks like. And I'm a little bit, like I said, I'm a little bit behind on grading those things.
Yeah, and I can imagine with the whole Blackboard interface, it's got to be incredibly time consuming.
1C and 1D. Yeah, okay, so the 1C and 1D should have been graded already, yeah. So yeah. I will go back and fix that.
Okay, thank you.
I haven't graded anything from like this section yet. Like
yeah, I didn't think so.
And the 3A.
Yeah.
Professor Stevens, where do I find my test?
It should be in your Blackboard under, where is it? What is it called? Like course tools or grade center? It's under grade center in mine. I'm not sure what it looks like from the student perspective. I think it's under course tools. Or course materials. It's like towards the bottom of the Blackboard.
Whenever you go to Blackboard, click My ACC at the top, and then where it says Tools column, it should be like the 5th one, and it says My Grades. And then you just click on the map.
Thank you.
Mm-hmm.
Okay. Yeah, it's under the Tools tab, I believe. If you go to the course Blackboard. Ooh. Yeah, there are 33 students still enrolled in this class. So, think a graded 30 test, something like that. The tests take a bit of time. To be honest, like the homework is a little bit quicker because the homework actually pops up on Blackboard. The test, I have to like all download the test. And then there's a few dorks that still didn't turn in with like a PDF. They did a JPEG, so I had to do like Photoshop, put some stuff on there. It took some time. So I hope you really read those things. But I think we need to start getting on the stuff that we did, or the stuff that is due today or tomorrow, the stuff that we're supposed to do today. Okay, so they give us this big table, table 3.4. The section is about like the CPI and comparing prices across times. And so this table might be a little weird, but they're kind of dividing this up. And if you wanted to put your lines like that, that might make sense. Because they're going year by year, 77, 78, 79, 87. They're coming back around here and going up years. And then they're coming back around here, going up years. So they're kind of splitting this table. They're doing the year in the CPI, year in the CPI, year in the CPI. So if they give us a year, we should be able to pick the CPI off of this table is what I'm hoping. Okay. And they have a few different formulas, but like I think the easiest sort of way to get at these problems is just to write the equivalent fractions. So if someone needs 25K to maintain a certain standard of living in 1986, how much would they need in 2016? The 2 years I want to compare on this thing. If I want to know how much things have grown, fix that up. If I want to know how much things have grown from 1986 to 2016, the way I do that is I go to my table and I pick off my CPI. So my CPI for 1986 was 109.6. And I want to compare that 109.6 to 2016, which is 240. And this will get me the rate of increase from 1986 to 2016 is what this is doing. And so now the question is saying if someone needs 25K in 1986, so where am I going to put that 25K over here? Am I going to put it on the top or the bottom is my question.
The top.
I'm going to put it on the top because it is a 1986 price. And so what would I put on the bottom over here then?
X or Y or something.
Yeah, put some sort of variable over here. So if we have two fractions and they are equivalent or the equivalent ratios, how do we figure out what X is? What's probably the easiest way? Probably to grab this thing right here and this thing right here. So you can try to find common denominators. There's that whole process of finding common denominators. But if you have two fractions equal to each other, the easiest way to find a common denominator is just doing that cross multiplying. You'll actually get the same thing as if you try to find a common denominator. So if we do, okay, that is like what, 4 zeros, 240 times 25K, 6 zeros. I believe it's giving me 6 million. And then this thing, if I want to solve what my X is, I have to take 6 million and divide it by 109.6. So we've done stuff sort of similar to this when we did similar triangles, but I'm getting something around 54,744.5. 0.52, and then I'm going to round it up to 0.53, ending in a 5. So I'm going to round that up.
You say 6 million divided by?
So we're doing 6 million, and we're dividing things by 109.6. I think the book probably gave a different way to figuring these things out. They would shift like one thing to the other side or something. So I think the book would go about saying this is a 1986 price. If we want to go from 1986 to 2016, I think we have to multiply by 240 over 109.6. I think that gives you the same thing. So I think this is the way the book would set it up. But they're doing that. It's the same setup as what we did. They're just doing it. They're just shifting certain values over. If you do your equivalent fractions, you should be able to solve all these problems. You might have to do an extra little step, but it should get you there. And then I want to like step back for a second. Does it make sense that I would have to make what, 54K in 2016 when I was making 25K in 1986? Just kind of knowing generally what you know about inflation.
I think so.
Yes.
Yeah, it makes like relative sense, right? You expect to go up. Okay, and let me double check. What was it, 17? Okay. Yeah, they're rounding it to the nearest dollar in the book. We're rounding it to the nearest cent, so I feel like we're better. But anyway. The next one, 19. What was the overall increase in prices due to inflation as a percentage from 95 to 2005? So if we want to find the rate of inflation, which is what it sounds like what they're asking here, how do we find the rate of inflation? What is the rate of inflation? What's another way I could ask for that? Because it is a type of change, but what type of change?
Relative.
Yeah, it's going to be relative change. Relative change of CPI. And so if we're taking the relative change of CPI from 95 to 2005, I'm going at 95. I'm looking at 152.4. And I'm going up to 2005, which is 195.3. So I'm going up to 195.3. I'm doing the relative change. So we've talked about this before, but I'm subtracting 195.3 minus 152.4. Divide this by which of those numbers?
195.3.
You got to divide it by your reference. So your reference should always be this guy right here. 152.4 should be the thing you're dividing it by. It's the thing you're starting off with. It's the 95. We're going from 1995 to 2005. We want to find the relative difference. It's this thing. The only other thing I might put there is like to a percentage. So this, I'm definitely going to go and lunge after a calculator or probably cry myself to sleep because that is 42.9, 152.4 is what I'm trying to do here. And so dividing that by 152.4. I'm getting something like 0.28. 1496. I don't know. I haven't decided how many I want to round it to yet. And so we still got to convert this to a percentage. So this should be somewhere around what, 28.15 if I want to go somewhere around there. What is this telling me? From 95 to 2005. What is this telling me?
Is that how much inflation rose?
Yeah, that's the rate of inflation right there. There's about 28% inflation. So what, 42 out of 152 should be about 30%, somewhere around there. Okay. So rate of inflation is the relative change of your CPI. So that is something you might have to kind of commit to memory. Like you might have to remember how to find inflation. You might have to remember that it is relative change. Yeah, what's that?
Was that 28.14%, correct?
It should have been 28%.
Oh, you rounded it.
Mm-hmm.
Oh.
Yeah.
So do you always have to round it?
I mean, that one is getting rounded already by your calculator, so I don't know. Rounding it to 2 to 3 decimal places is usually pretty good. And I mean, in the end, like rounding it to 2 to 3 decimal places, right? So, calculators definitely come in handy for these sorts of things. I definitely would not want to do some of these numbers by hand. Some of them I'm not sure you're going to be able to do them by hand. Okay, so we compared prices across time. This, we're going to compare prices across cities. So this is very, very similar to like the sort of CPI thing that we're doing, but instead of having like a time component, we're having like a distance component, right? We're doing different cities, but it is the same thing, right? If I have a CPI in a certain time, it is the same thing as that CPI in a different time over the certain time in a different time when we're talking about the indexes. And so we could essentially move this thing over here, right? And is what I'm kind of seeing. We can have a price and other towns. If we divided this same price into town, is equal to the index of other. Out of room on my paper. But we could think about these things as equivalent sort of ratios. If we go other to years, we're going other to years. That's the same thing. They just move this thing over here and you get the equivalent ratio. You multiply by your price in your town is going to go over to the other side and it's going to look like this equation. So this is the same equation as this equation. I'm just rewriting it is all I'm doing. It is an equivalent ratio. If we just get those equivalent ratios, I think that might be the best way to sort of just go about these problems. There are shorter ways. Like I said, you could use this one probably. I think we'll go with this one for these. So the price in other town equals the price in your town. Index of other over index in yours. So for a house valued at $400K in Phoenix, find the price of a comparable house in Miami. Price in Miami. That's going to equal to the 400K. And now I got to think about how to set up this ratio. And we're going from Miami to Phoenix, or from Phoenix to Miami. So who's next to my total on top? Who's my it on bottom. Better way to fill this out. So whose index should go on top?
Phoenix.
It should be the other town. So what is my other town in this example?
Phoenix.
Miami.
It should be Miami. Yeah. So this is the Miami would be the other town. The your town would be the Phoenix price. So the other town is Miami. The your town is Phoenix. You could probably set it up the other way around, but I'm trying to set it up in the more straightforward way to solve it. So this one has to be the Miami. And again, this is the one that they're going to give you, and this is the one you want to convert to. Okay, so we're grabbing these values from the table. This is 400K. I'm going to multiply this by the index of Miami, which is 161, and divide that by the index of Phoenix, which is 122. Okay, so I'm going to do this all at once. But we do 161 over 122. That should give us like 1.319 or somewhere in that ballpark. I guess I can write that middle of the step. Somewhere around there. I'm rounding it. And then we're going to multiply by 400K. So I didn't round it in my calculator, so this is not going to be coming out exact. This will be exact. This won't be exact, I guess is what I'm trying to say. 527,868. And like 85 cents is what I'm getting. And so we're thinking about this thing. And if you're rounding things a little bit, as long as you're within a few dollars and you're doing all the steps correct and you're showing your work, you should get your credit for it. I'm not trying to like really count off on rounding stuff. If you're like going 500K and you're like $1 or $2 off, that's fine. If you're going 500K and you're like a couple thousand off, then I'm probably going to say something, right? And so it's this rounding thing is really like in context of like, what are you rounding? How much are you rounding? And what is the problem sort of thing? How far off from the problem are you getting, I guess? So for a 400K house in Phoenix, would it make sense that that same house in Miami would be around 500K? Yes. Knowing what you know about the road out there, hopefully that makes a little bit of sense. A house in Miami is going to cost you a bit more than a house in Phoenix for the same quality of house, right? Miami is a little bit more of a hot spot than Phoenix, probably. It's a busier port. Compared to the ports of Phoenix, it is way busier. Sorry. Okay, so that is that table. I don't think we need that table after that, to be honest. I could be wrong. I think all these other have their numbers in them. So total spending on healthcare in the U.S. rose from 85 billion to 3.2 trillion in 2015. Compare the relative change in healthcare spending to the overall rate of inflation as measured by the CPI. So the first thing they want us to do is to compare the relative change in healthcare spending. So the healthcare spending went from 85 billion to 3.2 trillion. And so there's a few ways I can do this.
Can you please turn off your mic, Alyssa?
Can I do what?
Turn off her mic, because every time she some noises in the background, it smalls your when the thing goes small, it goes to the top because the sound of her, whatever she's doing.
You should be able to pin. You should be able to pin the video if you double click the video, it should pin the video so it doesn't change the video. You got to make sure you're in speaker view, and then you just double click the video and it pins the video. It'll put a little pin on there. That work? Total spending on healthcare in the U.S. rose from 85 billion to 3.2 trillion. So there are a few ways you do this, but we're going from 85 to 3.2 trillion. This is billions to trillions. Did I do that right? This is thousands, millions, billions. Gotta go one more.
How do you lock the screen again? I'm sorry.
You double click on the screen and it should lock it, I think. Is that how you do the pin?
You can go to the three dots. Like if you put your mouse over his video at the top, the three dots, and it should say pin.
We're doing the 3.2 trillion minus 8 billion. So if you want to work out all your zeros, I guess you could do that. And then we could divide it by like 8 billion. I'm not gonna do this. Like that's probably not the way I really want to do this. If I just make everything in billions, I can just take that thing relatively. It might be a little easier. What, 3.2 trillion? If I do things in billions, it would look like 3.2 trillion. And I have to subtract, what, 8? Another way you can do this is I'm getting rid of, what, 3, 6, 9, everything. 6, 9, 3, 6, 9. There's just too many zeros there. I don't know what to say. But if we're doing everything in billions, 8 billion is 8 billion. 3.2 trillion would be 3,200 billion. Is another way to think about this. And we're going to have to divide everything by 8. And now we're about to figure out why everyone's broke. 3,200 minus 8 is going to give me what? 3,192? Divide this by 8. This is giving me 399. Jesus, is it is high? Which one? This is problem 31. How are they getting that?
Yeah.
366. Did I get those numbers correctly off the problem? 32.
I think it's supposed to be 85 billion.
Did I mess that up?
Yeah, it is.
Okay, cool. That might make a little bit of difference. All right, this should say 85. That's where they're getting that number from. I was like, that's not adding up to what they got. Okay, so this helps if you write down the right number from the problem. Okay, so this is what, 3,115 over 85, I think is what this is simply out to be. 3,115 over 85. Which is still pretty large. Not quite as large as what I was getting. But this looks like 36.647. I didn't even write it on this one, but we have to convert this to a percentage now. So we still have to move this 2 decimal places. 366, 4.7%. And I believe that's what they're getting in the back of the book. They grounded 3665, I believe is what they did. So again, what this means is that medical expenses went from 85 billion to 3.2 trillion. They went up 3,664.7%. Okay. If you were to take a guess, do you think this is going to be larger or smaller than the CPI between those years?
Yes.
Yes, definitely larger, right? So if we go between, what 2 years are we going between now? 97 to 2015, 77 to 2015. So we're going from 77 to 2015. So it looks like 60.6 to 237 is what we're doing. So we got to do the relative change between this number and this number. We are doing 237 minus 60.6, and then we're going to divide this all by this thing we started out with, which was 60.6. And then I got to convert my decimal to a percent. So it's 237. Okay, so I should be getting something like 176, like what, 0.4 over 60.6. And so this part of the equation is giving me something like 2.91. I haven't done the thing, I keep deleting it. But after I do this, I have to convert it to a percentage for a relative increase. So if I move this thing 2 decimal places, I think I should have 291%. So then they probably want you to step back and like compare and contrast these. This is like what, about 300%. So this thing went up about 300%. Wow, the medical cost went up about 3,000%, something like that. Are there any questions over these problems, over how we're finding what the relative increase of the CPI, which is also known as our inflation? So you find the relative increase of the CPI, that is your inflation. So I think that's a big thing to take away from this probably. The other thing is we got to find relative increases of something like this and this. So you got to convert these things to maybe in billions. So or you're going to end up writing a bunch of zeros. But if you put everything in the base of billions, it might save you some of that elbow grease. Erasing those zeros, I don't know.
The professor, so I could just use, when you're speaking on the billion, just use the first 4 numbers. I mean, the first 4 numbers. And add billion there to it instead of just writing all these numbers down.
Yeah, we're multiplying this thing by what, 1,000 to get to billions?
Yeah.
We got to move this thing over 3 decimal places to get to billions. It might save you a little bit of time. You could write out all the zeros if you really wanted to. If you really like doing that, that's something you could absolutely do. It'll get you there. Not the cleanest. Okay, so 33 private college costs, so according to the College Board. So we did healthcare costs. We wanted to know the inflation in healthcare costs. I think this is a very similar problem, probably, if I remember correctly. But now we're doing private college and public college costs. According to College Board, the average tuition and fees at a private four-year college and university increased from, and they're going to give us an amount in 1990, $8,396 in 1990, and it increased to $33,480 for the 2016-2017 school year. Calculate the relative change in private college costs over this time period and compare it to the overall rate of inflation as measured by your CPI. Are they done? Ooh. So we're going from 8,000 to 33,000. So I hope right now everyone's got like out a sheet of paper and they're like writing this thing down. I want to do the relative change from the 8,000 to the 33,000. So hopefully you're attempting to try these like on your own a little bit. If I want to go from this one to this one and I want to know the relative change of these two things, woo, 33,000. Going to subtract 83, which is my reference. I'll compare this to the 96. The thing I gotta do is convert to percentage. So this is how I get my relative difference. We've done a few sections over relative difference. Well, we've done at least 1, 2. So here's at least the third one. It's got it in there. It'll come up a few times. So it is a concept that you will have to learn at some point, probably, if you want to get good grades. So 25 is what I'm getting. 83.36 is what I'm getting for the rest. I'm dividing 25,084 by 8396. That's giving me like 2.9876, somewhere in that ballpark. 2. That's like the sloppiest multiplication sign ever, huh? And I'm really lazy about doing this, but I should probably really throw some equal signs to show these things are equivalent. I got to convert this to percentage. I got to move this 2 decimal places. I think I'm getting something like 296%. And so this is telling me there is an increase, and that looks like an almost like what, 300% increase? So if something is a 300% increase, that means it's 3 times as much. If we look here, you might notice that's about 3 times as much as that thing. So maybe you could like kind of eyeball something sometimes and sort of check if you're in the right ballpark. But that is our increase. Our relative increase from the 8,000 to the 33,000. So that was the first thing they're going to ask us, is find this relative increase of these 2 objects. Now they want us to compare the relative increase of those 2 objects to the relative increase of the CPI, or the rate of inflation. So now we're going from 1990 to 2016, I believe is what we're going to. They might be going to 2017. I think they're going to 2016. Let me write it down, and I will double check. Oh, it's got to be 2016. We go to 2017. Is where we're going. We're going to 2016, which is 240. The other year they give me is 1990. So I'm looking at 1990. Which is right here, which is 130.7. So I'm going from 130.7 in my CPI up to 240. I want to know what the relative increase of these 2 things are. My relative amount has to be that second one, the 130.7. Okay. And so now I'm doing this. I'm trying to find the relative difference 240 minus 130.7 is going to give me like 109.3. And I'm going to divide that by 130.7 multiplied by 100% to get a percentage. And there might be some things you can take away. If this is smaller than this one, then we should be getting a fractional amount here. 8.3, what, 6? It's probably pretty good. And if this thing is fractional, you might notice that when we go and move the decimal here, this thing should be less than 100%. And so how does this compare? So let's go back to this one. This was what, from the 8,000 to 33. So I think the cost of education at a, was this one the private one? At a private institution was the first one. The second one's a public institution. It is basically the same problem. So 298, it went up by about 300%, while the rate of inflation was only about 83%. So what's the takeaway from this sort of thing? Education costs too much, right? Is that what they're trying to say? I think so. I think they're trying to say like healthcare and education are like increasing way too much. Kind of what they're saying without saying it, right? When it's increasing 300% and your rate of inflation is only 83%. There's I don't know. Maybe there's a reason for it, but it really shouldn't be increasing a lot more than the other goods, right, around it. You would expect these things to go up kind of symmetrically, and they don't. Why is that? I don't know. Politics, probably, right? Okay. So we did the private college. We're going to do the public college now. I want you to look at this public college. I want you to go ahead and do it. Okay, we're going, they're doing a 4-year from 1990 to 2016. So we're going from 19 to 2016. Hey, guess what? We already found out the rate of inflation for that guy. So we have already done half of this problem. Congratulations. We know what the rate of inflation for this time period is. There's one sort of thing that I want you to write out. I want you to go on your own paper and write it out. We're doing the relative change from 1780 to 9650 is what we are doing. And so I'm hoping you have this formula written out on your own paper. Get this thing down somehow. 9650 is the thing I'm going to. I want to subtract 1780. And I want to divide this all by the thing that I started with, which was the 1780. So this is the one sort of thing I really need to calculate for 34. I've already got my rate of inflation. So 9650 minus 1780. And I'm going to divide that by 1780. So I'm getting 7870. If I subtract these two things, I'm getting 1780. Got to convert it. If I divide these two things, I'm getting something like 4.421. And I still got to convert it. And so if I convert this to a percentage, I'm getting something like 4 to like 0.1. I think this one is even like what? It's even worse than the other one, I think. The other one was about 300. This one's about 400. So private went up, but the public went up proportionally at a higher rate. Why is that? Because you can't be having your populace get too smart now, can you? So, questions about this, how to find this? Is anybody else as mad as me that the prices are going up for healthcare and education? Okay. But I hope there's a sort of takeaway here. One of the things we can sort of talk about or use math to talk about is like sort of injustices and like social inequalities that happen, right? If you want to talk about social factors, you're going to have to know how have some kind of basis and understanding of statistics to do so, right? In order to have a sort of reputable sort of point being posited. In order to talk about like the changes in purchasing power and of those things in that nature and social power, like you have to have like an understanding of these sorts of numbers.
Professor, I have a question.
Yeah.
So basically the formula that we're doing here is what we did in 3A, which is that new minus old divided by the old.
Exactly. It's the same old formula.
Or
what they say, something minus reference over reference. I don't remember what they use, the words. Compared, I think is what they use. Compared minus reference. Same formula. Going from one thing to another, we're dividing it by the thing that we start out with. And so I guess this has a time factor, but it doesn't necessarily have to have the time factor, right? Okay. Whew. Any other questions? Are we getting this stuff down? This is basically the same formula you're writing those equivalent fractions, right? Which is something we've kind of done already. Silence is always really scary. I don't know what else to tell you. Like, when I get any questions and you just don't hear anything, it's like either they understood all that or they are so lost they don't even know what to ask. You know, it's like one of the other.
Question.
Yeah, what's up?
So basically, when the second part of the question is compare it to the overall rate of inflation, is there like a particular way that we're supposed to be wording that, or should that give us a clue as to like what formula you're trying to use to compare it, or you just like?
No, they just want you to compare the two numbers. Is one of them larger than the other?
Okay.
So like,
I don't think it's not that we don't speak. It's just that we have to really pay attention because you move fast. So, I mean, I don't want to disturb anything. I just want to make sure that I'm getting this while you're doing this, and and when you express it. So I'm like right there with you, but it's just that I can't really say nothing because I really need to listen to what you're saying because you move pretty fast.
All right. And so
Christopher, sorry to interrupt, Mr. Sievers, but Christopher, to that point, I've actually found it pretty helpful to kind of pay more attention to the things I'm having problems on during the lectures, and then you can re-watch them to kind of catch up and correct yourself. It's time consuming, but anyways, what were you saying, Professor?
So they're just asking you to say this one is more than this one is basically all they want.
Okay, cool.
Say that the rate of education is increasing more than inflation.
Got it.
Just kind of comparing which one is larger.
Okay, that's what I thought, but I always kind of trick myself into thinking that they want way more than what they're asking. So
yeah, I had a weird kind of tangent thought. Do you ever think about like animals and like how much math animals can do? Like
I mean, they're probably really good at estimating.
Yeah, well, I mean, like if you put out a food bowl in front of a dog, right, and you put out a food bowl with more food and less food, they're gonna realize like that one with more food has more food. So like already there, that's an inequality that they're setting up in their head, right? They're like, this one is more than or less than. But I mean, it is. It's an inequality of what they're doing. So they understand like inequalities to some degree, right? Like, do they understand? I don't know. Who knows? There was that lab, and it was on a PBS thing, and he had like, I don't know, hundreds of toys or something like that, and he knew the name of every single one. And then they threw a new toy in there that they never told him about, and it was like a little Darwin doll. And they're like, go find Darwin, and he figured out which one it was. He's like, well, it's not any of the ones I know already. It's got to be the new one. So that's already like a deductive sort of logic that he's like processing in his head, you know? It's kind of crazy.
That's really crazy. Thanks for sharing.
Yeah. It's an old PBS. You could probably find it somewhere. I don't remember what it's called. But I remember it had Neil deGrasse Tyson in there before he became famous. The prices in the table are not adjusted for inflation. So revise the above table to express all prices in terms of 2016 dollars. So you can write equivalent ratios. I think I wanted to set up my formula. If I want my price in 2016, price in the year X or Y. I want to do CPI or index. You're doing gold prices now. Okay. So do I want to put gold? Comparing. But I want to know what year. So what year am I putting on top? Am I going to put year X or am I going to put year 2016?
This
will be the 2016. This is the converted to. This will be the year X. And if you want to do this with equivalent ratios, you could actually absolutely do this with equivalent ratios. I would give you 100% either way. Price in 2016 to the price in year X should be the same, right? The dog's snoring over there. Okay. 2016 gold and X. And I know I'm like abbreviating words and throwing words out probably. So I hope it still makes sense. I'm putting the important words in there at least. But okay, so we're doing three different things: the price shown in table 9 just for inflation. Revise the above table to express all prices in terms of 2016 dollars. Oh, got it. See, it sounds kind of annoying. Oh no, they're not doing gold. Are they doing this with CPI? Okay, never mind. I'm lying. We're not doing gold. CPI. Convert their price to gold. I read it wrong. Sorry. I've been reading a lot of stuff today. I read a lot of stuff today. We're doing the price of gold in year in 2016. The price of gold in year X. We got to do the CPI of 2016 over the CPI in year X. Going back and grab this table again. Not that table, the other table. This table. So let me rewrite this so it's a little bit cleaner. So the price of gold in 2016, what we want to compare. And then we're going to do the price of gold in year X. And we're going to multiply this by the CPI of 2016 over the of year X. So this is the sort of formula that I'm thinking about. If I want to find the price of gold in 2016, the price of gold in 1986. So I have to do this 4 different times. So I'm going to do the same thing, and it's going to look very similar. I'm just going to swap out like 2 numbers each time, I think. So I'm going to go with 391 was the price of gold in year 1986. My CPI in 2016 was 240 from the table. And they gave me the price of gold in 1986. The other price I have to look at is the price in 1986, which is at 109.6 right there at the bottom. So we got these 3 numbers, multiplying and dividing. 240 divided by 109.6. And then I want to multiply that by 391. And so I'm going to kind of crunch this all at once. So hopefully you have a calculator, do a calculator check. 56.2. And so if I were making up this table, what I would do is I'd take this 856.20. I would probably come back to here. This has what, 856.20, so I can map out that I did that one already. So I have this work. That's what I did for the first one. So the next one is not 391. That number changes to 369. The CPI in 2016 is still going to be the CPI in 2016. So this part is not changing. But that thing on the bottom, we changed years. So now we are talking about year 1996. So guess what I'm going to have to do? I'm going to have to go to my table to 1996. I'm going to have to look at that number is 156.9 that I'm looking at. So this is 156.9. And so I hope you notice this, and this is where we were going with this. These 2 years have to match up, and these 2 years have to match up, is the important sort of thing. The common thing people do is they will flip this, and they will end up getting it wrong. So we're going to multiply by 240, 369, times 240, divide by 156.9. So you might also notice it really doesn't matter what you do these, and you can do the multiplication of these 2 and then divide. I think it should give you the same as if you divide and then multiply. So there are actually a few legitimate ways to do this, but you should get 564.43 is around 0.44, I believe.
Professor, can I ask a question? On 391, I did the, I'm not trying to stop it, but under the 140, 109.6, I came up with 85617. So what did I do wrong?
So it might just be your calculator's rounding things a little bit. If you're 3 cents off on $800, I don't think I'm going to care about it too much.
Okay.
As the gas station policy, take a penny, leave a penny, I guess, right?
So can I add? Okay, so I'm just gonna keep.
I think it's probably your calculator doing it. Just rounding decimal places is probably what it is.
Oh, okay.
It's what it sounds like. So this is 564.44. We're halfway done. We're almost there. Oh wait, we're more than halfway done. 2016. Guess what? This guy is already in 2016 prices. This guy still got to convert. And so now we're looking along here. It's the same pattern that I've been using. Where did all my paper go? Here we go. So I'm still doing the same thing. I'm going to take that number on the table, which is now 636 now. I'm going to multiply it by something. I know the top number is 240. The other number, I'm going to have to go look in the table for 1996 now, is what I'm doing. 2006. Sorry, I did 96 already. I got to go look on the table for 2006. When I go look on the table for 2006, it's that number right there at the bottom, the 201.6. So this looks like 240 over 201.6. Okay, so if I do 636 times 240, and I divide that by 201.6, this is giving me somewhere around 757, and two decimal places, 0.14. So this is the final number I really got to put in my table, 757.14. Whew. Okay, so the prices shown in the table are not adjusted inflation. Revised above table to express all prices in terms of $2016. So you might want to look through like my slash mark, but it went from like 381 to 369. So I don't think it went down here in price. It went up in price. It went up in price. If we don't account for inflation, if we do count for inflation, well, it still went down and it still went up. So it may not always be going up or going down at the same rate, right? If we count for inflation. So we do maybe have to check. See that it's still going down and up accordingly. If you bought 3 ounces of gold, and this is price per ounce is what they're doing. So this is the price of gold per ounce. So now if we bought 3 ounces of gold in 1986 and we sold it in 1996, would you have seen a profit? How do we figure that? This is 44. And it's not. It's really easy if we have it all in the same price, I think. So if we bought 3 ounces of gold in 1986, how would you look at that? So if it's $856.20 per ounce in 2016 prices, how much would that be for 3 ounces?
It'd be 1908.
56. How are you getting them that times? Where are you going 1908 with this? I'm not saying this, 391. How are you getting that number?
I was just timesing 636 by 3, but it might be the wrong number actually.
Okay, so if you do 636 by 3, that would give you price in 2006. Is that what you're doing? We're doing part B, so we're going from 86 to 96 in this one.
I thought we were supposed to do A and C on 44.
Oh, is that what it says? It says, that's right. I forgot. I was doing everything.
I'm like, wait a minute, what does he have? He's supposed to be a C.
Yeah, what I would do, I would do like 3 of 1996. And so if I were doing part B, I would not do the prices that they have listed in the table. I would do the prices that we just found, because if you do the prices that they list in the table, these do not account for inflation. So they don't really tell you whether you're making like money when it's adjusted for inflation. So if you want to do this, I would do it with the prices we just found. If we go 3, we bought 3 ounces in 2006. That would be 3 for what?
Is it 757.14?
Yeah, I'll go to 757.1. We bought 3 of these things for 757.14. The bought price, and what did we sell it for? 3 times the 1152, which is in 2016. There's a few ways to do this, but what we're doing is we're looking at the differences. Another way to look at this. Increase that much per ounce over those 10 years is another way you can do this. Or you could subtract what? You could subtract that amount that you bought minus the amount that you got from when you sold it. That's absolutely another way you can do this. 1152. 1152 minus 757.14 is 394.86. We're multiplying this thing by 3. It should be 1184. I'm out of there. Here we go. And would you expect to make a profit on this? Well, just in general, like without even like crunching those numbers, would you expect to make a profit if the price went from what 757 and it went up to 1152? And this is adjusted for inflation, right? These are prices that are adjusted for inflation now. If it's going up, do you expect to make a profit off of this?
Yeah.
Yeah, hopefully, right? So, and I said it, we can do it together as like one sort of thing. We can subtract and multiply them by 3. The other way, and I guess I'll go ahead and like write them out here. 3 times 1152. The amount that we sold is what, 34? We sold them for. The amount that we bought them for was 0.14227. 1.42. If we subtract these two numbers, we should get the same amount, right? Is what I'm saying. How much you sold them for minus how much you bought should give you how much you profited off of them. Revenue minus cost is the profit. Either way, we should be getting something around, you should be making around $1,000 off of this thing. Close to 12, huh? Questions about this one? We have one more section left. We have like 5, I think maybe 5 problems in that other section. They are a bunch of tables we're going to look at. There's basically Simpson's paradox, and then there's like the testing, the mammogram testing sort of problems that we're going to go through. Okay. So that was all about CPIs, finding rates of inflations. These are things you should be able to do. If we ask for the rate of inflation, it is the relative change of your CPI. So we're looking at this, Josh and Jude. And so in the homework or in the notes, they gave us the batting average in a really weird sort of way. It's like almost like a percentage, but it had an extra 0 in there. It was like batting score, maybe. It was called something different, maybe. This batting average, you can kind of see how they're doing it, but if we do 50 divided by 150, that's going to give us a third or 0.33. 10 over 50 is going to give us this 0.2. So the way that they're getting the batting average, and they're kind of calculating and giving you a lot of information here. 35 over 70 is going to give you the 0.5. But who had the higher batting average in the first half of the season? So if we're looking here, whose batting average is higher? God, that's almost like too easy of a question for this class.
Yeah, Josh.
That's Josh. 0.33 is 0.2. Which player had a highest average in the second half? Not everyone at once.
Josh.
Josh, okay. Still Josh. So
this is question 11, right?
This is what? Number 11 is what it is, yeah. 3E number 11 is what it should be. What player had the higher overall batting average for the season?
Josh.
Yeah, you would think, right?
Yeah.
Okay. That might be a problem. Thinking might be a problem. No. So we want to calculate Josh's hits to his at bats. So if we look at his hits, he's got 50 here and he's got 35 here. His at bats are 150 and 70. So his total hits to his total at bats. 5 over 150 plus 70 is what, 220? And so we're probably doing this on a calculator at this point. But I'm getting like 0.3864. We're going to do the same thing with Jude. So we want to do her total at bats. So I'm hoping like y'all try to get just like a step ahead of me on this one. Try to figure out how we're going to do Jude's right before I write the numbers down. I'm going to take her hits, which is 10 and 70. I'm going to do all of her at hits, or all of her hits on top, versus her at bats on bottom, which are 50 and 150. So 50 plus 150. This is going to give me, what, 80 over 200? 40%? I think it's even 0.40. So now that we've actually crunched these numbers, it might be easier to answer this question. Who had the higher overall batting average for the season?
Jude.
It's got to be Jude. And does that seem confusing? It might be a little bit confusing, right? Because you're looking at Josh, you're going, hey, first half he's better. Hey, second half he's better. Surely, like in the whole thing, he's going to do better. But no, like it doesn't happen that way, right?
Professor, can I see the
these numbers?
Yeah.
Okay. So, and in a bit on like why it doesn't happen that way, it does have to do with like they have different number of at bats. So he did like better here with the 150, or she did better with the 150 bats, I think, and did slightly worse with the 50. He did slightly worse with the 150, but did probably better with those 70. So he did better with like the smaller number sample. So I'm not expecting you to construct these. I'm not expecting you like it's a difficult thing to do, to figure out what numbers you're going to add together that are going to make it larger here and smaller there. Like I'm not expecting you to figure out the numbers themselves. Like, but you should be able to do something like this. If I wanted to look at piece by piece and divide it into halves, the first half and second half, Josh is going to do better. You should be able to crunch these numbers like this and figure out that overall Jude's batting average is going to be better. So we got this thing that seems paradoxical in nature, like it seems to contradict itself. Briefly explain why they might seem surprising or paradoxical. So what is this thing called? If you got this question, there's like basically one word I'm looking for.
Simpson's paradox.
Yeah. I ask you this question and you put Simpson's paradox, I would probably be happy. You know what it is. You know what it looks like. And there's a few like examples they can give with this. One of the ways I've seen is like they will do ambulances and versus like an ambulance versus a helicopter, I think is one of the examples I've seen before. If you look at it the correct way, it looks like the helicopter's probably killing people, even though it's the better option usually to save people. If you split it apart, it looks like it's worse, I think. And if you put it together, it looks like it's worse. If you split it apart, you realize that they're actually doing a pretty decent job. There's one of Berkeley's admission policies and gender biases that's also a really famous example of Simpson's paradox. important thing is that you notice that it's Simpson's paradox. I think all the rest of the problems, they seem kind of like they might be the same thing. Not the Simpsons. It seems like the rest of the problems are the same thing, and they're not Simpsons, I guess is what I should say. It seems like they're all sort of the mammogram things now, I think. I could be wrong. No, this might be a Simpsons still. Which state had the higher scores in both racial categories? So the table shows 8th grade mathematics scores in Nebraska and New Jersey. They're separated according to race of the student. Also shown are state averages for all races. So they have the test scores. And they say which state had the higher scores in both racial categories. So we're comparing Nebraska to New Jersey. So we're comparing 281 to 283. So it looks like New Jersey was higher here, 250 to 252. It looks like New Jersey was also higher here. So it looks like overall, what they're asking for here. What state has the highest score in both? So this one, New Jersey was higher, independently, if we look independently. But if we look at for all of them, it looks like Nebraska's coming ahead. So I think they're kind of asking us in a weird, so which one had it in both categories? I think this one, they want the New put them in categories. New Jersey is going to have the higher one. But if we don't put them in categories, Nebraska is higher. Explain how a state could score lower in both categories and still have a higher overall average. So what's a factor that could be making this up? Oh, we got 3E exercises. And we're talking about Nebraska versus New Jersey. It might be a little too accurate with this one. What do we know about Nebraska and New Jersey and their racial composition that might be making this possible? So just like having a basic sort of knowledge of demographics, right? Nebraska is like what the quote unquote, like it's a horrible name, flyover state, right? It's not a lot of people there. Not exactly the most diverse compared to like New Jersey would probably be a lot more diverse. It's on the coast right there next to New York. And so we would expect probably like the non-white population in New Jersey is going to be larger, right? What do they say in the back on this one? Let's see. 13, they say the percentages of non-whites is significantly lower in Nebraska, which is the same thing I just said, just the other end of the coin, right? And they say the following table gives the actual percentages of whites and non-whites in the state. Use these percentages to verify that the overall average test score in Nebraska is 277 as claimed in the first table. So what I think they're doing, let me double check. So I think they're doing 87% on that first one. 13 or 250. Okay, yes, that's how they're getting us. So the following table gives these percentages. So we know Nebraska looks like 87 and 13%. So 87% is going to be white and 13% is going to be non-white. And so this is sort of like the weighting thing that I was talking about. These are going to be weighted more than these, right? And if we want to know how they're getting these numbers, the way that they're doing it is they're going to weight this one 87% and they're going to weight this one 13%. So if you take 87% of that first number and you add it to 13% of that second one, you should be getting that average. And that's what I'm getting. 0.87 times 281 plus 0.13 times 250 is going to give me the 276.97. I round that up to the nearest decimal, to the nearest whole number, but it would be 277. I want to do a similar sort of thing for New Jersey. This one is going to account for 66%, and this one is going to account for 74%. And if I do this, hopefully I can verify that this is the same number, is 252. It should be giving me 272.46. This one is a little bit of a weird question, if I'm being honest. I probably wouldn't ask you this. Just the way that they have two tables and they're putting them together is just a little bit weird. But it makes sense to what we were talking about. And why does this seem like contradictory? What is this an example of again? Someone say that word again, please. Yeah.
The Simpsons paradox.
Woo, there it is. It's the Simpsons paradox. Don't have a cow. So use the racial percentages to verify that the overall average test score in New Jersey is 272. As claimed, did we just do that? Yeah, okay, they said verify this one, verify this one. We did that, briefly explain why it seems surprising or paradoxical. Because it's Simpson's paradox. Okay, that's all the questions they asked. I really thought they asked it all in one go, but they split it apart into multiple parts, I guess, huh? So there were two examples of Simpson's paradox, and then I think we're gonna have like three examples of the like mammogram sort of testing. So you can do mammogram testing, you can do drug testing, you can do polygraph testing, you can do. Are we going to do trial by jury? I don't think we're doing jury testing, but like it would be very similar, right? We have a reality. Either there is a cancer or there is no cancer. We have a test that tells us there is either cancer or there is no cancer. Same thing with like a polygraph. It is the table is set up very similarly. You either lied or you didn't lie. And in reality, you either lied or didn't lie. The test will tell us either you lied or didn't lie, right? And so I went over this. I went over the table. You can have true positives. You can have false positives. You can have true negatives. You can have false negatives. So there's ways that these can lie. There's ways that they tell the truth. Okay, and then they got this thing. Okay. So 17, let's go with this. So like table 3.7, the following table is based on assumptions that the incidence rate of breast is 1%. Verify that the tables in the number are correct. So the 1% means that out of everyone, 1% of these people will actually have cancer. So if we look in the table, we're looking at the number of people that actually have cancer versus the total number of people overall. So we're comparing these two numbers is what we're comparing. So if we go 100 to 10,000, this should be 0.01 or the 1%, where that 1% is coming from. So if they want you to verify it, that's what they're talking about. That 1% is the first thing they give us. There's an incident rate of 1%. They say this thing is 90% accurate versus Oh, the previous table was 85. Okay. So now this thing is 90% accurate. So 100 out of 10,000 is giving you the 1%. Now we're looking here. If you have cancer, what are the odds that it will detect it? Would be this 90 out of this 100. Given that you have cancer, what are the odds it's going to detect it? This is going to give you the 90%. So there's two numbers really that you have to verify as a like percentage. There are like 5 numbers that you should verify like through summation probably. If we do 90 plus 10, it should give us 100. If we do 990 plus 8, 9, 10, it should give us this one. So we do have to check these totals as well. I don't want to really have to. 90 plus 10 and 100. I gotta check out that 9 and 0. 8. Check that is 99. So I'm checking down. I'm looking at the sums down. I also have to look at the sums across. So this should sum up. These two should sum up. They do. That's not too hard to do. 8, 9, 10 plus 10 is 8, 9, 20. And then the last thing is this thing should sum up. Your total should sum up here, and it should sum up across here. These are all numbers we can check to make sure our numbers in the table are going to be correct. Suppose a patient has a positive mammogram. And so when we do these problems, there's some information that they're going to give you. That information is probably going to help you reject a lot of these numbers. It's going to help you narrow down where you're looking. So the first thing is they say, suppose you have a positive mammogram. Guess what? I'm only looking along here now. I'm looking at those 3 numbers. Supposing you have a positive mammogram, now they're going to tell you some other quality. So we're supposing we have positive. What is the chance that you have cancer? So how would you build that probability?
Is it 90 over 1080?
Yes, it's 90 out of the total. And we chose 90 because those were the people that had cancer. So I know you thought you're just going to come into math today and you weren't going to talk about anything fun, but today we're going to talk about cancer. No, sorry, cancer. So horrible joke, but it is a horrible thing. So hopefully it's not too bad. I've known quite a few people who passed away from it. So. Okay, so 90 out of 1080.
Hey, Professor, I just gotta say, yeah, your classes are exciting, man. They're fun to be in. I really like it.
Okay. Thank you. 90 out of 1080. So how do they have to? The patient has a mammogram. What is the chance? So how would you say this? 90 out of 1080. 8.33% chance. But this gives you good information, right? We want to talk about cancer. We want to talk about the scary things. Every once in a while, we got to talk about the scary things. And this gives you good insight into what those sorts of tests mean. I did it in the notes, so hopefully that gave you some insight. But given that we have a positive mammogram, what are the odds that we actually have cancer? There's like an 8% chance. So you go to the doctor and he tells you your mammogram came up positive. Do you freak out, I guess is the question. It's certainly scary probably if you get a positive mammogram. It pops up positive, it's like definitely puckering up a little bit, right? But how much? How scared should you be? there's only an 8% chance you have the thing, right? So there's almost like a 92% chance you don't have the thing. So like, what do you do if you have a positive mammogram? What's usually the first thing they do?
Test you again.
They test you again. And I kind of said this in the notes, like a mammogram, it's a lot better at rejecting the fact that you have it than it is at confirming the fact that you have it, right? And so we like to do multiple tests to kind of see if we can't just kind of reject it. What is the chance that a patient with a positive mammogram? So now we're going to positive. Given they're positive, what is the chance that they don't have cancer? And I kind of said it already. It should probably be around 92%. But we're taking that 990 and we're comparing that to the total now. So now we're doing 990 out of 1080. So they're still giving us a similar setup, except now we're doing the people without cancer. Still given that they have a positive mammogram. I'm getting like 0.9166 repeating. About like what, 91.67% is what I'm talking about. So if you got a positive mammogram, it's actually better odds that you probably don't have the cancer. But the other way around, which is probably what they're asking next, suppose you have a negative mammogram, what is the chance that you have cancer? So now they're supposing it is negative. So now, can I get another line? Let's try to sandwich this thing. So now what I'm looking at is this line right in here. So now they're supposing it. Well, now you can't see the titles at the top, but I'm ignoring that line in the middle. I don't need to look at those numbers. I'm just looking at this numbers on this row. So suppose you have negative. What are the odds that you do have cancer is what they're saying. So what's my total here? What total am I going to use? What's my denominator for the negative mammogram?
89.
It should be what?
89.
Should be 89.20 is the total. And out of that, they want to know that they have cancer. So which one of these would be the ones that have cancer? These ones would be the ones with cancer present. Would be the 10. Yeah. You're trying to find out what the 10 out of the total of 89.20 would be. Ooh, so we did 10 out of 89.20. This is giving me 0.0011121. If we convert this to a percentage, it's like a really small percentage. And so this is, given that you have a negative, what are the odds that you actually have cancer? They're going to be really, really low, right? So if we get a negative test result, it's a pretty good indicator that we can reject the fact that we have cancer. There's going to be a really, really slight chance that we have cancer, right? Is what this is telling me. And so this is going back to, like I said in the notes, if you get a negative test result, it's a pretty good indicator that you can reject the fact that you have it. So can you still have it? Absolutely, right? But it's a really small chance. There's like no guarantees in life, right? We can give you certain probabilities and things, but not a lot of guarantees. Okay. So that's 17. I think we did all of them in 17. Suppose a patient has a negative mammogram. Polygraph test. So this will look very similar to the thing we just did. Whether we're doing a mammogram, a polygraph test, or a drug test, we're comparing some sort of reality to what a test tells us, basically. And then there's that type 1, type 2 error that I briefly mentioned in the notes. You kind of trade out one for the other, right? So the stricter what test is one way, or the more lenient it is one way, it's going to give you one error. It's going to either give you more false positives or false negatives. Results in table are from experiments conducted by Charles Hantz and Gordon Barland. Okay. In each case, it is known whether the subject lied. So the table indicates when the polygraph was correct. So they did some kind of experiment. They had people set up to lie. They had some people set up to tell the truth. How many subjects did the test find to be lying? Of those, how many were actually lying and how many were telling the truth? What percentage of those who were found to be lying were not actually lying? So that asks like 3 questions right there. So how many subjects did the test find to be lying? Polygraph test indicated that the subject lied. So they don't have totals here. So if you want to put total columns, you can do total columns. One, two, three, part 2. So how many subjects did the test find to be lying? So where are we looking at? The polygraph test indicates that the subject lied. We're looking at these 2 numbers. So how many were lying, or how many did the test say were lying? Can we read that from the table? Is that something that makes sense?
42.
It's going to be 42, and it's going to be.
So would it be 57?
57.
It would be both of these. We got to add them together. So they don't have totals in this one. So if you want to do totals, you would do like maybe a total column over here. So we got to do our totals. This is 57. And I'm going to go ahead and do it. I don't even know if I need to do it. 41. Right, would be 9 plus 32. And then the other thing is the totals of the totals. If I want to know how many people total in this experiment, I would have to add these 2 together, which would give me 98. And I could do totals here. And they should also add up to the same 98 if I do it correctly. So this is what, 7, 47. This is 51. And if I add 47 and 51, they should add up to 98. So if we want to do totals column, it might be a good idea. It might be a good idea to do them. Sorry, I'll get it out right eventually. So how many subjects did they find to be lying? Overall, they found a total of 57. They found 15 that didn't tell a lie, and they found 42 that did. But the test said there were 57. The next thing says, of those, how many were actually lying and how many were telling the truth? So 15 and 42 are what they're asking for. So these 15, did these 15 people lie?
No.
No.
And
So
the 42 told a lie.
So there were 15 that were truth tellers. There were 42 that lied, and it detected that they lied, is what this is asking. The next thing they ask is, what percentage of those who were found to be lying were not actually lying? So this test found 57 people to be liars. Polygraph. So your test is telling you there's 57 liars. We know that, what, 15 of them were telling the truth? So how do we find that percentage? Looking at the 57 that we detected. That's not too good. This is 0.26. Woo! And this is about 315. if we round that to percent. So that is telling you that's over 25% of the people. That's over 1 in 4 people that you're like accused, right? It's not very good. To me, that's not a very good strategy. I think. Are we going to 235 in this class? We got like one more example after this one. I know like it's the end of class, so if you got to burn out and watch the video later, I completely understand. But we got one more after this problem, so it shouldn't take us too much longer. If you want to stick around, I'm definitely going through all of it. So with that said, if you were in charge or something, I don't know, would you be comfortable administering this polygraph to people? I don't know. To me, this would make me uncomfortable, right? You're accusing a lot of people, and a lot of people percentage-wise over the people that you're actually catching. In order to catch people, you're convicting a lot of people just to catch a few people, basically, right? So not a good approach. And I kind of mentioned this in the notes, but like polygraphs are not admissible in court. There's reasons why they're not admissible in court. This might be part of it, right? So how many subjects did the test find to be telling the truth? So now, and I think I probably inadvertently kind of figured this out. We're looking at here what the polygraph is our test. Another way of saying you're telling the truth is saying you did not lie. So that's saying the same thing. So the polygraph test, how many people did it determine to be telling the truth? So what's the total it's giving me?
41.
41, how many people told the truth? The next thing is, of those, how many were actually telling the truth? So I might have to move this. Did the subject actually lie? People that are telling the truth are not lying. So we're looking in this column. And which of these numbers am I looking at?
Nine. 32.
Should be the 32. So I'm looking in this column, and I have to be looking in this row. They're giving me that the polygraph said they didn't lie, and how many didn't lie would be the 32. So it cleared 41 people, 32 of them were telling the truth. What percentage of those who were found to be telling the truth were actually truthful? So now we want to know the percentage. They're trying to piece it together a piece at a time, I think. But how do I find that percentage? It is the 32 out of the 41 is what I'm figuring out. So I'm trying to figure out how many of those people that it said were telling the truth were actually telling the truth. And I'm getting like 0.78. Somewhere in there, so about 78% is what I should be getting for this thing. Which is probably not exactly the best thing, right? If you're trying to determine if someone's telling the truth. 78% is not a very accurate sort of thing. And in general, like we have a court system, we tend to like prefer people like the innocent until proven guilty approach, right? We tend to not rule heavily on the guilty side. We tend to think it's better to let people kind of go than it is to convict someone falsely, right? Or so that's how our court's supposed to be set up. I'm not sure everyone gets the same treatment, but pretty sure everyone doesn't get the same treatment. Put it that way. But that's the way it's supposed to be kind of set up. So the last thing, we have one last problem, number 23. Whew. So we got a game. And I think this is the politician math or whatever the heck they try to throw in the end of this section. Give numerical evidence to support the claim that Spelman College has a better team than Morehouse. Give numerical evidence to support the claim that Morehouse has a better claim than Spelman. Which claim makes more sense and why? Okay. Are they just looking? What are they looking for here? Are they looking for? I think they're looking for home games. So we're gonna have to find out what their rate is, and I think this doesn't sound like a mammogram problem, if I'm being honest, right? It's not saying the reality versus the test. So I think what they're doing here, if I were to take a wild guess.
So are we differentiating between home games and away games?
It's not really, yeah, they're differentiating and they're categorizing things by home and away, right? And so we're introducing categories. This is going back to that first thing we covered. This is absolutely a Simpsons paradox example is what they're trying to get at here. So in order to do this, we're going to have to find our averages. So if we want to find the winning average, this is 10 wins. How would you find your winning average here?
Add your wins and your losses for their total games.
Yes, that's exactly it. So 10 out of 29 is what I'll be doing here. So 0.34. This is where I'm getting this. 3448, somewhere around there. I'll do 4 decimal places. If I do this, I have to do what? 12 over 16, I think is what I'm doing. Woo, 16. So I have to add the wins and losses for the total games, and I do 12 over 16 to get the wins over the total games. This is going to give me 0.7. So I'm just figuring out for the individual games at this point. 9 out of 28 is what I'm doing. 6 out of 76 here, I believe. So this is 0.32. This is giving me 56 out of 76. Should be pretty high. 0.7. About. So if I'm looking at Spellman versus Morehouse, Spellman had 0.34, Morehouse had 0.32 on home games. So who did better on home games?
Spellman.
It looks like Spellman. Who did better on away games? It looks like it was also. Yeah. Question? So it looks like the away games, it looks like Spellman also did slightly better, right? 0.75 versus 0.74. So if I want to do part A, I would figure it separately. If you figure it separately or in categories, categorize. By home and away. Spellman is going to be better. And you should really write out these numbers to show me that you know what you're doing. You're calculating, crunching these numbers, and figuring out that Spellman is better independently, right? Categorized and separated. Spellman does better. If we want Morehouse to do better, okay, so now we're going to have to look at Morehouse versus Spellman. If we look at the total games here, we add all the games, wins and losses. We do 10 plus 19 plus 12 plus 4. 10 plus 19 plus 12 plus 4. There are 45 total games. So there's 45 total games. How many wins? And we're looking here, 10 and 12 is going to give me 22 wins. So 22 out of 45 is going to give me what the heck Spellman's is 0.489. It's like 4.8 repeating. The other guy is Morehouse. Morehouse, their total is going to be 9 and 19 and 56 and 20. 9 and 19 and 56 and 20 is going to give me a total of 104 games. Out of 104 total games, they had 9 wins and 56 wins. I believe that gives me 65 total wins. I have to tally everything up. I have to tally up the totals. I have to tally up all the games for the total games. And I have to tally up all the wins for their total wins. And if I do 65 over 104, I'm getting 0.65. So if I want to brag on Morehouse, what am I going to do? I'm going to look at all their games combined. Okay. And then they ask, which claim do you think makes more sense and why? So how would you say these people are better? Which one would you say was better? That's kind of a hard question, to be honest. This is 23. But if you know anything about sports, it might help. Maybe, I don't know. Typically, when you talk about a team, do you talk about like separating them into home and away victories, or do you talk about their overall score? Typically, when we talk about a team, we would probably talk about their overall score. They would probably say Morehouse is a better team. Like, it shouldn't matter how we categorize things with home versus away, right? Typically, when we talk about how good a team is, we mean how good they are regardless of where they're playing. So I think that's the final question that we have in our homework. I hope that did a pretty good job of sort of reviewing these concepts. They are a bit different. It might take a little bit of practicing, but